Okay, YouTube, in this video I'm going to introduce the concept of a rational function. We're going to start pretty simply, but we say a rational function. What do we mean by rational function? The root word here of rational, of course, is ratio. And when we talk about rational functions, we're going to define them as any function of this form here where we say our function of x, f of x, is actually equal to p of x over q of x, where I'm going to make a note here. We say p of x and q of x, they are polynomial functions. So remember, when we discuss polynomial functions, these were these things that, you might have like 3x to the fourth plus 2x squared plus 1x minus 4. That's like a polynomial function because, you could see that our exponents here in standard form are always going in descending order. We have a degree, we have a leading coefficient. We're basically going to be saying, well, this function that we're looking at, this rational function, is the ratio of two polynomial functions, okay? And how they behave with respect to one another kind of dictates what our graphs look like and how they behave, okay? So let's go ahead and take a look. We're going to actually look at y equals 1 over x before we do any other rational function, because we could say here that what we have right here is a 0th degree function y equals 1. And down on the bottom we have a polynomial function y equals x, and when I divide both of those I get this rational function 1 over x, and that's what our y equals here. So if we said, well, how would this behave? The interesting thing is I've actually already put this in over at desmos.com. We say y equals, and I put a over x. I'm going to put in a 1 here. 1 over x, okay? And if I turn this on here, we can see a graph. And as a matter of fact, if I were to say make a table out of this here, we say duplicate it and make a table, you can see that when x equals 1, well, we get y value of 1 over 1, which is 1. So you can see that this point here, 1, 1's on our graph. But the interesting thing is, as x continues to get bigger and bigger, if I were to put 1 over 2 now, I would get 1 over 2 is a half. Okay, it'd be a half. And if I were to do 1 over 3, I'd get a third. Roughly here you'd say, you could see that I get a third. And then, 1 over 4 would be a fourth, and then a fifth, and a sixth, and so on and so forth. What you see is we get this graph that as x gets bigger and bigger, our y value is going to continue to diminish. And this is kind of like what we talk about when we talk about inverse variation, as a matter of fact. But as our x gets smaller and smaller, you can see our y values getting bigger and bigger. As a matter of fact, you notice that when we plug 0 into this, we get y equals 1 over 0. We get an undefined value. So essentially, what we see here are the basic characteristics of this graph. Are the right side here, it kind of is centered at the origin. You can say 0, 0 is right here in the middle. But it goes through 1, 1, and it has, a couple of asymptotes that exist. We have one at x equals 0, because we could never plug in 0 and get a y value back. It'll be undefined. And then we also notice here that there's an asymptote on the x-axis, because no matter how big of a number we divide by for x, we're never going to arrive at a height of 0. So essentially, we get this right branch of our graph here with those two asymptotes. Now, if we were talking about the left branch and why it's symmetrical, if you were to plug in a negative 1, you would still get 1 over 1 as you did with 1 over 1. It's just that it was a negative 1, and so you can notice how these y values or outputs down here are the same as the outputs up here. It's just that they're opposites, okay? So one thing that is important to note about rational functions is often we say these are hyperbolic graphs here, and these are the branches of a hyperbola. But what we could essentially say is this: they have some level of symmetry to them, okay? So if you know one side, you often can determine the other side, okay? So here's our basic parent function here of a rational function. So some things we want to comment on, and these are things that I've listed over here. But we say the x-axis is a horizontal asymptote, so we have a horizontal asymptote right here. And we have a vertical asymptote that is the y-axis, okay? And we have two branches that approach those things. We say the domain and range are all non-zero real numbers, everything but 0. So in other words, as far as the domain goes, we say all x values. You'll notice that on our graph here, it goes from left to right forever and ever, except for there's one x value, which it doesn't. That's x equals 0. And so we'd say the same thing is very true about the range. It goes through all y values except for this one here, y equals 0. We say the graph has two symmetrical parts called branches, okay? And it says for each point x, y on one branch, there's a corresponding negative x and negative y on the other branch, and we observe this over here. So after kind of messing around with that, what I want to do essentially is this: we want to be able to comment on all graphs of this form right here, and I'm going to actually make this more general. What if instead of y equals 1 over x, could I make a statement about all parent functions of the form y equals a over x? And so in the past I've said, well, graphing activity, let's do this. Let's graph y equals 2 over x, 3 over x, and then negative 1 over x, and negative 2 over x. What I can do now is actually, I just want to show you guys this. If I were to go over to Desmos here, and I'm going to put in, instead of 1 on top, I'm going to put in a. And a is going to serve as a slider, and I've put in a table as well. You can see that I've got some points here. I'm going to highlight all these points here. There's 1, 1, there's 2, a half. Here's negative 1, negative 1, negative 2, negative a half. And you can see that I can alter the value of a. The idea is that when a gets bigger and bigger, let's say we make a equal to 2. What happened is that all of the values in the table doubled because we're taking all the initial values and now we're doubling them. But also this, you notice our graph got a little bit more vertically stretched. So in terms of key points on our graph, we say instead of going through 1, 1, it's going through 1, 2. I want to make a general comment about this. We see that we have a branch here on the right, but will it always go through 1, 1 or 1, 2 was our a value was 2 this time? What if I made a equal to 3? Will it always go through like 1, 3 if the a value is 3? And I would say that in general, we could say that on this graph over here, we would say that it's always going to go through, and I think I want to sketch this in here, it's always going to go through the point, and let's list this in, 1, a. And it's very true down here. If you have symmetry, at least of graphs of this form, it's going to go through -1, a as well because of our symmetry. Now, as far as what it goes through at 2, you'd have to go plug that into the function. We have to say, well, what is f of 2? I got to go plug that in. But I can promise you it's whatever the a value is here. So you'll notice that the bigger a gets, a is 4, it's going to go through 1, 4. That's kind of a gimme. And then we could plug in another, x value into the function, see what we get here. I would say if x is 2, you get 4 over 2, and 4 over 2 is 2. But you can see it's getting more and more stretched the higher that gets. But we still have asymptotes on the x and y axis, and if we were to make this negative, the only thing that happens is, it would go through, say, a is -1, it would go through 1, -1. We could plug in 2 and find out that it goes through, 2, -1/2. But you would see that your branches just flip over and it's reflected, okay? So the a value is really important here. The only reason I bring that up is because what we're going to do now is we're going to extend this understanding and say that really y equals a over x. Okay, I see how this graph behaves. It goes through 1a. I can plug in the x value 2 and find another point, and I know that it has asymptotes on the x and y axis. The only thing we're going to do in this function here is admit that h and k exist, and they represent horizontal and vertical translations of our graph. So just as we normally have it, we have h is a companion of our x value, and k is this floating value on the outside. But let's admit a few things here. We say h is horizontal translation, and we say that k represents vertical translation, so we say vertical translation. And as always, you see that the k value has a plus in front of it, so it's going to be honest, whereas the h value has a negative in front of it, it's going to be dishonest. So what we're going to do is we're basically going to get into graphing functions of this form here. Y equals -2 over x plus 3 minus 1. This is our rational function. And instead of having to make a table every time and plugging in so many values, we're going to say, you know what? I'm going to graph its parent function first. So when we refer to its parent function, we're going to say a function that exists with no h and k. And if I were to just cut h and k out of this 3 and this 1 here, I would get -2 over x. So what we are going to do is we're going to use all the basic characteristics of this graph over here that we're kind of observing to draw this parent function, and then we're going to shift everything. 3 to the left here, it looks like our h value is -3 and our k value is -1, okay, and down 1. So essentially what this graph would look like, let's start here. I'm going to draw like a really light, maybe we'll do it like a pea green or something like this. Really light green graph that represents our parent function. And our parent function, I recognize, already just has asymptotes on the axes here. And we're going to be moving these anyway, so that's why I wanted them light. And we say, okay, well, -2 over x, I know that at 1, when x equals 1, and I think we should table this out here. When x equals 1, then if I plugged in 1 here, I'd get -2 for an output. Now, this is something we totally expected in the first place. Whenever it goes through 1, it goes through 1, a. And in this case, our a value is -2. But we'd say, now if I plugged in, say, 2, what would I get? I get -2 over 2 is -1. So I'd say, well, 2, -1 is on our graph. And what we're going to do is we're going to take this graph here, we're going to say, well, this is the right side. And if I were to draw the left side, well, if 1, -2 is on here, then -1, +2 is on this other branch. And if 2 right, 1 down is on here, then 2 left, 1 up is on this branch. And we see that we have this upper branch here. So this is our parent function. Haven't done anything else to it yet. What we want to do now is we want to apply these transformations, okay? So what we're going to do is we're going to take all these points right here and we're going to shift them, in this case 3 left and 1 down. All right, so we're going to go 1, 2, 3 left, 1 down. This is going to go 1, 2, 3 left, 1 down. This point here, go 1, 2, 3 left, 1 down. This point here, 1, 2, 3 left, 1 down. So we've shifted all our points. The thing that's important to note is that the asymptotes shift also. So in terms of left and right, let's think about this. The left shift is only really going to have an impact on our vertical asymptote because it's the one, it's going to go left 3. I mean, if you shifted left 3 on the horizontal asymptote, you wouldn't be able to tell the difference. So we're going to go left 3, and we say that our vertical asymptote is now here, here, and this would be now the same thing as our h value. I'm going to say that in general, x asymptote is always going to be there, and our y asymptote has to go down 1. So it was at y equals 0, now it's at -1. So here's this asymptote here. We say y equals -1, or in other words, y equals whatever the k value is. So with these in, we're going to sketch in our new graph. We say that here is this function right here with its branches, and the last thing we'd always want to do is describe, say, domain or range. So as far as domain or range, let's get used to something here. With rational functions, you're going to say a whole lot of this: all real x, all real y. And then what we're going to do is we're going to put in an exclusion. So we're going to say colon such that, and we say that the x value we're going to exclude here is that x cannot be -3. If we were to plug -3 into this function up here, we'd get -3 plus 3 on the bottom, which is undefined. And we'd say also here y cannot be -1. You see this here on our graph. It'll just get really close to -1 but never quite reach it. But that is basically what rational functions are and what their graphs look like and their basic behaviors, and how you would graph one if it had transformations. In the next video, we'll look at what happens when you divide a linear function by a linear function specifically, and then we're done with this section. Cheers.